Welcome, everybody. Tonight we're working on Unit 9. The topic for tonight is reinforcement learning. We're looking at really kind of two main tools or strategies. Q learning is the primary one that we're looking at. There's also this other technology called GIM, if you will, from OpenAI. That's a really important one, too. There's a lot of developments happening in this area actively these days. What I would always caution all of you is, like, if you really want to dig into any of these, please look at the sources for any of the slides. This particular slideshow has a lot of material in the notes section of the slides. And when I say that, I mean, like, if you're looking down here and you look in the non-presentation mode, there's a lot of information, links, additional content, answers to some of the questions on the screen. Not all the slideshows have that, so I get the feeling that some higher level people put this together and spent a lot more time on some of these slideshows than some of the previous ones that we've seen. All right, so I'm going to just take us here right to the agenda. I am going to go into presentation mode because the videos seem to operate better in that format. And please never hesitate to ask questions along the way, even if it's unmute and ask or type in the chat. But if I miss anything in the chat, please let me know. Once again, the main topics for the evening. And just to kind of refresh our memory here, we've kind of gone through a few different types of learning or training models, basically, including supervised, unsupervised, and now we're entering into reinforcement learning. And you view these in a lot of different ways, but the reinforcement learning is, I feel, really suits the modern world pretty well. It suits how like we as humans intuitively operate if we're not given information to start with, or even if we are given information to start with. And this is not a quiz or a test, right? But you should start at this point to understand, at least with these first two, right, what these mean now, right? And guess what? We're gonna talk about it. So supervised learning, all right, just a refresher, right? In supervised learning, things are labeled for you in advance, right? This is a dog, this is a cat. And that's helpful, right? When you're like a young child and you're learning what to do, that somebody tells you what something is very helpful, right? How else would you really know, right? You need a frame of reference, and that's what this gives us. It says it works by learning how to differentiate them into respective classes, and you're providing label data into a neural network. Essentially, you're telling the machine what it's supposed to see. And if you want to, instead of machine, say the child, that's a cat, that's a dog. And I think that's a really good thing. All right. In unsupervised learning, the information is a little different, right? We're not labeling the data in advance, right? We cluster the data into similar groups or data sets. So when certain things are like other things, these oranges look alike and these bananas look alike and these apples look alike, right? That type of thing. And granted, there's variances within them, but generally they're clustered together. There's no specific goals or targets. It says the machine uncovers similarities within the data, right? So it depends on the data that you're feeding it. So reinforcement learning is in its own category, but ask the questions that they show here. What do you still recall from unsupervised learning? I mean, it was just like 2 weeks ago, right? But it's amazing how quickly you can let that stuff slip out of your head. But what you're going to notice here, and the process of the instruction that's designed here, is really to introduce you to these topics, deepen your knowledge of them with every iteration. And as we move forward, we got to remember that all the new areas of AI that we'll be learning. So like in our follow-up course to this, which is natural language processing, it is a deeper subset of machine learning, right? And computer vision is a deeper subset of those, right? And that's kind of the rabbit hole that we're going down. The other thing that I'll say, and I'm just going to pause the video momentarily to say this. All right, so we're going to focus on reinforcement learning. So let's like move forward here and start absorbing some of the the content. Now, from a graphical standpoint, like, you know, and I don't know if you guys recall, like when we were in the intro to Gen AI or the intro to AI class, right? We started talking about machine learning and all its subsets. And then we saw these complicated diagrams. And you're like, oh my God, I got to learn all this stuff, right? And I want you to review supervised learning, um, unsupervised learning, and look at some of the things that come off of them. Like, oh yeah, we did talk about that. Oh yeah, we did talk about that. Right. So I'm hoping that you guys are recognizing the fact that we are getting through the material, and as we move forward, it will go deeper, right? And the subsequent courses are part of that. When you start to do a comparison behind these, I want you to notice, you know, some similarities between reinforcement learning and supervised learning, and that is these little loop backs here, right? So with supervised learning, we start with labeled data, right? And then we map it, you know, to some sort of output or whatever. We have certain targets and we deal with errors and we try to minimize those. In unsupervised learning, we're just clustering information, right? We're classifying it, if you will. With reinforcement learning, we look, instead of data with or without labels, we're looking at states and actions relative to them. Real big comparison when we do reinforcement learning, you know, is kind of like playing a video game. Like, how do you learn how to play Mario? Well, you start and you fail and you keep trying, and it's like, oh, you got to jump and then hop and then, you know, whatever. And so you evaluate what went right and wrong. And if it went right, there's a reward. If it went wrong, it's a negative response. And then that teaches you how to take an action, right? All right. So that stuff is all at play here. A lot of terminology, a lot of math, a lot of symbolism, but I want you once again to focus on the higher level topics here. We're not here to like grill you on the math. Eventually, when you guys move on to your bachelor's and master's degrees, which you all should, right? And I always encourage people to do that. Please do that. You know, the world needs you. You know, we need smart people out there. You know, so this is a branch of machine learning, as it says. Trial and error is the approach, right? And it says to achieve a goal in a complex environment. And there's rewards and penalties for every action that you take, right? So if I like put my hand in the cookie jar and a mousetrap clamps on my finger, that's a negative reward. But if I reach into the cookie jar and I get that chocolate chip cookie I want, that's my reward, right? And the reward is I get to eat it, right? And you learn really quickly which jar to put your hand in and which jar to not put your hand in. And that's kind of the mindset here overall. We look at a bunch of different things. So there's all these little letters and subletters that they use. T stands for time, S stands for state, R stands for reward, A stands for action. Right? You'll notice that state, reward, and action all have a sub number of time, so that they happen at points in time. So a certain action at a certain point within an environment or like the space we're working within creates a new state. So like if I take an action, now we're working in a new thing and we have a new possible reward. And we keep doing it over and over again and until we figure it out, basically, you know. And with the models that we use to do this, when we first start out, we're always exploring. We're always trying things to figure out what works and what does not. There's no rule set to start with, and I think this is why this is kind of interesting. This is a thing that does overlap a lot of other disciplines. That's the point of this, right? So you look at how people have done this in all these different areas: computer science, neuroscience, psychology, economics, math, engineering, right? How have people figured out how to do all these miraculous technological things in the modern world? It didn't happen all at once. Bottom line, right? It's like, hey, what happens if okay, I guess I won't do that again, or I will do that again, right? And if you think about that's probably how we got here as human beings, is a lot of trial and error. It's like, hey, I wonder if I eat that plant if it'll kill me. well, it killed Joe, so I'm not gonna eat that one. You can, why don't you try it? That type of thing. And you think about that, yeah, that's the approach. Um, what's interesting about the reinforcement learning, I mean, at least in terms of a concept or a conception, it does come from animal psychology, right? And if you guys have pets, right? So if you have a dog, and we consider cats kind of untrainable, but they're trainable too, right? But dogs way more so, right? So like, and a really great example is I was walking the dog last night, and she's pretty good. I can usually walk her without a leash, and she'll heel, she'll listen to me, she'll turn, she'll stop, she'll sit, all that stuff. But sometimes she's like motivated by, I don't know, bodily function or the smell of a rabbit or whatever, right? And she'll pull on the leash, and then I have to like remind her, it's like, hey, you should be right here by my side, and I will correct her until she's like, okay, oh, all right, I'm not getting away with it. I better listen, right? But trainable, right? So that's why it comes from there. Later on, they kind of combined this with really technological fields like programming, right? And that's how we got to this kind of like little sub-science, basically, reinforcement learning. It's a little bit different than other approaches, because it says like supervised, unsupervised learning. You have to have data. You have to have you have to have knowledge of what the data is and what it means, maybe even how to solve the problem ultimately. But when you are in more complex, and it says your large complex problem spaces, sometimes those don't work well, right? Because they don't account for like the outliers, for example. You might have things that are happening that you can't predict, and you might not have enough data on those things you can't predict to really deal with it. So reinforcement learning is really about being adaptive. Ultimately, it's being able to think on your feet, and adjust to a situation. And I think one of the really interesting aspects of this technology that we're learning, all this artificial intelligence, is the fact that all of you, I think, are intelligent in studying this stuff, right? Because it is intriguing, and we are, driven to use it. And I think that if we don't learn how to adapt to this new world that's rapidly adopting it, we will all get left behind, right? And so all of us, I think, are very adaptable people just by nature of being in this class, and I think that's kind of an interesting thing, right? Not that you have pre-existing knowledge of it, but hey, we're building that knowledge one little piece at a time. That's what we're doing, right? And don't ever freak out to it. Hang tough and flow with it. When do you use this? When your system, it says, is too dangerous for physical trials, right? Like if you're going to train a car how to drive itself, it might not be a good idea to just put a car out in the road, smash it, and go, oops, that didn't work, and then have to build another car. It makes no sense, right? You might want to do it, through code or something instead. Or you're dealing with really large state spaces, and it says the vast number of permutations within the game of Go, right? And that's that game that's like way more complicated than chess. I've never played it. Has anybody here ever played that game or tried to play that game? I've always kind of meant to put it on my bucket list of games to try, because I'm a really big fan of playing chess, and so for example, like if you play checkers, you quickly figure out, there's like 30, 40 scenarios, right? If you play chess, there might be a couple hundred scenarios, and you do get to learn them, right? But with Go, there's so many permutations that human beings usually have a very hard time mastering it, which is why it's cool, right? Because it's very variable. Or the last bullet here, seeking to augment human analysts by optimizing operational efficiency. And it says the decisions that business analysts have to make for supply chain efficiency. So if you're looking at how you're flowing your raw materials in through a finished product, I mean, where do those raw materials come from? Well, I mean, you might have tons of choices, and every little bit of the supply chain is highly variable, and that can make so many differences to how you do things, for sure. All right. Coming up here, they're going to give us some examples of reinforcement learning through a series of videos. And I think most of these videos are pretty compelling. I'm going to play them. Some have words and music and some don't. And try to analyze like what's happening here. And I want you to notice here, this comes from Stanford's Autonomous Helicopter Air Show #2. So this little, RC powered or whatever it is, helicopter flies itself. There's no human controlling it. So let's just run the video here, right? And just watch this thing. Oh, not good, right? Oh, not good. Oh, okay. Upside down, not good. Sideways, not good. Straight down, not good. Right. If you guys have ever seen a helicopter fly, they usually try to stay pretty level, right? Right. So this one's trying to teach itself how to like, okay, how can I fly and not crash? It must have some little algorithm in there. It's like, don't hit the ground. Maybe they could teach you not to pollute so much. Flying backwards, sideways. Right. And basically what it's doing is it's trying a bunch of different things to figure out how to stabilize itself without being told in advance what it's doing. Okay, so that's what that one is. So let's move on to the next slide. All right. All right, so let's watch this one. This is based on Google's DeepMind AI, and it says just taught itself to walk. Let's watch this one. Sorry about the ad. I would filter that out if I could.
Big ideas.
Right. You can read the words, so I'm not reading them to you. But what they're showing you here are animations where these, pseudo objects or beings or whatever you want to call them taught themselves how to make the maneuvers, like going up a stair or going from one platform to another, like in a video game or something. And they have to go through the trial and error process to figure out how to get around obstacles or to go over something or climb something or step or even just actually walk, right? um yeah, it is pretty funny, but like, you know what, would you like to see a video of yourself as a child learning to walk? Younger generations, you might actually have that, but us older people, it's like, unless your dad had like a Super 8 camera way back when, not happening. How about this one where AI learns how to park a car? You know what? This is a challenge for human beings too, right? And I always chuckle because I live in an urban environment and I park on the street overnight. So I can like parallel park in one maneuver, two tops. Okay, three or four if it's really bad or tight. But I watch like people come in from the suburbs and all they do is like park in parking lots and driveways, and I laugh because they can't do it, you know. But they do have cars that park themselves. Once again, we got an advertisement here for Wix. Let's get rid of that. All right, so here's a AI car. Randomly starts off. It's trying to find its way to the parking lot. Well, that's not a parking lot, right? Okay, well, it should get a penalty for that one. Maybe it could smash into the pole. Nope, that's not good. Yeah. Okay. All right, you fail. Right. And you can see like they're trying to show like some of the sensors. And this is virtual, mind you, right? So they're not doing it with a real car. And this is how they train autonomous vehicles. They create like kind of like video game 3D environments like this to teach the software model to finally get to the point where it's going to get into the parking spot. Okay, you smashed my pickup truck, not good. Eventually it will get in there and succeed, but there's a whole lot of trial and error. Classic old Atari games. Once again, okay, well, thank you, advertising. All right. Once again, this comes off of Google's DeepMind Q learning algorithms. It's going to play Atari Breakout. says that the AI agent is given necessary sensory input you see on the screen. It was ordered to maximize the score on the screen. No domain knowledge is involved. This means the algorithm doesn't know what to do to start out. So it gets 10 minutes of training and it figures out I can hit the ball. Sometimes the ball gets passed, right? It's got to figure out how to hit the ball, where to hit the ball, etc. And it just keeps going. And you know what? Like if you guys sit down and play a video game, it's kind of the same way, right? Like you play it, you try things, and now they're saying after 120 minutes of training, and then what is it going to try to do? Like if you know how to play this game, the trick is you make one narrow channel in the middle and get the ball to the other side, and it breaks out most of it by itself, right? That's always what I used to do with that game. Yeah. 240 minutes of training. Right now they're talking about what I'm talking about, right? They just they narrow in on one spot if they can. They can figure out how to get the ball at one spot and get it through, then it will succeed. I just want to see it happen. There you go. Right. And then you don't have to do anything. Okay. So I think that's pretty interesting. And then we have this AlphaGo thing. And when DeepMind was kind of like coming out to the public, and this isn't all that new, right? This is actually a number of years back. They trained it to play this game because this considered one of the more complicated games to play with the most number of permutations. All right, so once again, thank you, Wix, or not.
This is 2-Minute Papers with Károly Zsolnai Fehér. Hold on to your papers because this work on AlphaGo is absolute insanity. In the game of Go, the players put stones on a table where the objective is to surround more territory than the opponent. This is a beautiful game that is particularly interesting for AI research because the space of possible moves is vastly larger than in chess, which means that using any sort of exhaustive search is out of question, and we have to resort to smart algorithms that are able to identify a small number of strong moves within this stupendously large search space. The first incarnation of DeepMind's Go AI, AlphaGo, uses a combination of a policy network that is responsible for predicting the moves and a value network that predicts the winner of the game.
I do want to stop just for a second because he kind of gave us a clue there that instead of worrying about the whole thing at once, it's looking at simple, strong moves. Right, things that we know are going to work. Right,
after it plays it to the end against itself. These are both deep neural networks, and they are then combined with a technique called Monte Carlo tree search to be able to narrow down the search in this large search space. This algorithm started out with a bootstrapping process where it was shown thousands of games that were used to learn the basics of Go. Based on this, it is clear that such an algorithm can learn to be as good as formidable human players. But the big question was, how could it possibly become even better than the professionals that it has observed? How could a disciple become better than its master? The solution is that after it has learned what it can from these games, it plays against itself many times to improve its skills. This second phase is the main part of the training that takes the most time. Let's call this base algorithm AlphaGo Fan, which was used to play against Fan Hui, a 2-dan European Go champion, who was defeated 5-0. This was a historic moment, and the first time an AI beat a professional Go player without a handicap. Fan Hui described his experience as playing against a very strong and stable player, and he also mentioned that the algorithm felt very human-like. Some voiced their doubts within the Go community and noted that the algorithm would never be able to beat Lee Sedol, a 9-dan world champion and winner of 18 international titles. Just to give you an intuition of the difference, based on their ELO points, Lee Sedol is expected to beat Fan Hui 97 times out of 100 games. So a few months later, DeepMind organized a huge media event where they would challenge him to play against AlphaGo. This was a slightly modified version of the base algorithm that used a deeper neural network with more layers and was trained using more resources than the previous version. There was also an algorithmic change to the policy networks. The details on this are available in the paper in the description. It is a great read. Make sure to have a look. Let's call this algorithm AlphaGo Lee. This event was watched all around the world and can perhaps be compared to Kasparov public chess games against Deep Blue. I have the fondest memories of waking up super early in the morning, jumping out of the bed in excitement to watch all these Go matches. And in a long and nail-biting series, Lee Sedol was defeated 4-1 by the AI. With significantly less media attention, the next phase came bearing the name AlphaGo Master, which used around 10 times less tensor processing units than the AlphaGo Lee and became an even stronger player. This algorithm played against human professionals online in January 2017 and won all 60 matches it had played. This is insanity. But if you think that's it, well, hold on to your papers now. In their newest work, AlphaGo has reached its next form, AlphaGo Zero. This variant does not have access to any human-played games in the first phase and learns completely through self-play. It starts out from absolutely nothing, with just a knowledge of the rules of the game. It was trained for 40 days, and by day 3, it reached the level of AlphaGo Lee. This is above world champion level. Around day 29, it hits the level of AlphaGo Master, which is practically unbeatable to all human beings. And get this, at 40 days, this version surpasses all previous AlphaGo versions and defeats the previously published world beater version 100-0. This has kept me up for several nights now, and I am completely out of words. In this version, the two neural networks are fused into one, which can be trained more efficiently. It is beautiful to see these curves as they show this neural network starting from a random initialization. It knows the rules, but beyond that, it is completely clueless about the game itself, and it rapidly becomes practically unbeatable. And
all right, I'm going to cap it there. I mean, I think he's trying to get to the point of repeat here, but I think this is fascinating from a number of different standpoints, right? Being given the rules of the game, and then playing against itself versus playing against a human, right? Because humans can be prone to mistakes, but if you're playing against, another algorithm and you're going against the rules, and it doesn't take a lot of iteration. I mean, okay, granted, this is software running at the speed of light, training itself, but after, what did it say, 40 days, it gets to the point where like no human being can beat it. I think that's just crazy, right? Doesn't really make you want to play that AI ever, but it doesn't make me very curious about the game itself. It makes it seem like maybe I should learn this game, right? Because I do like games like chess, for example. So maybe that's the game for me. All right, let's learn some of the key terminologies here. And so these are important. The agent is basically the AI, right? It's the part that's making the decision, and reacting to the reinforcement learning. So basically, reward and punishment. The agent observes and interacts with the environment, and the examples they're giving here, like autonomous vehicles, or a humanoid robot trying to walk, or robotic arms trying to grasp an object, right? And those we'll call the agent. So in other words, the thing taking the action in the environment. Right? Then we have the environment. Like, what is the environment? Is it the whole planet? Is it a game board? Is it a video game environment? Like Mario's level or something like that. So we have a defined space within which we're working, right? Their examples are the board game of Go and the road for an autonomous vehicle, or the parking lot, or the sign that it's knocking over, right? Or the lawn that it's going over. Then we have the rewards, right? And I want you to notice here that they're calling it scalar feedback, right? So there's like a range of values, right? It could just be good or bad, but it could also be qualified numerically, maybe a kind of scale of some sort. So we figure out how well it's doing, how well it should behave. If it does well, it gets a reward. If it does not, it gets negative rewards or punishment. And the point is to maximize the rewards, right? And if you think as human beings, ideally that's how we learn too. But sometimes humans make mistakes and go back for punishment over and over too, right? I mean, you're here in school, that's kind of like punishment almost, right? Every time I go to school, I got to be lectured. Oh my God, I hate being lectured. Well, I assure you there's probably a reward at the end of the tunnel. So the kind of the point that they start getting into now with the rewards is the fact that, all right, so if you're looking for rewards, right? So every time you take an action, it happens over the course of time. And then you try something and then you repeat it. So there's one iteration, then another, then another, then another. And so like if I'm trying to get to like grocery store and I have more than one road I can take one road and then run into traffic or road construction or whatever, or it takes forever and I take another road and it's a lot more efficient, right? And if efficiency is the goal, the reward, then there we go, right? I do see that somebody had their hand up. Chris, was that you? You had a question?
Sorry, yeah. Just was this it was the slide before. I wanted to ask you what exactly a scalar feedback signal is.
Well, a scalar feedback signal would be, for example, um, like how strong a response is. You know, for example, like my example that I was talking about, like let's say driving to the store and you got like 5 roads you can take, and what you're looking for is which one will get you there fastest, or maybe which one will save the most fuel, right? And so the scalar feedback would be, okay, how long did it take? One took 10 minutes, one took 15, one took 25, one took an hour, right? It's a numerical value. So the reward is, you know, we're looking for the smallest number. So it's on a scale, right? It's measurable. It's not a yes or no. It's not, it's not like playing a video game where it's like succeed or die. It's like you're looking for a point value, like a maximization of something or minimization of something. That's how I would look at it.
Okay, I just looked it up on ChatGPT while I had my hand up there for a second,
Mhm.
and it did not explain it that clearly at all.
Yeah,
So
I'm
thank
sure.
you.
I'm absolutely sure it didn't. You know, and I try to like, you know, my goal, Chris, you know, is to kind of put it sort of in human terms that we can understand, right? Not get super mired in the formulas or definitions. And but whenever you have a scale, I mean, it implies numeric, basically. So here's kind of like, you know, the point I was trying to make here, right? Like if you can take 2 routes to a destination, right? Like so I turn on this street, turn on that street, whatever, and route one takes 38, right? Um, and if these are rewards, so maybe the rewards are fuel efficiency and time, and these are in a positive sense. If you get a higher value out of route one, I mean, you still get there with route two, but this one's better. Which route do you go with? You go with the one that's better, right? Yeah. Right. So that's an example of scalar as well. So they're giving examples of rewards here, like an autonomous car. The car gets to where it's going. Negative reward, it hits other vehicles, right? You know, we're not looking at how fast or how efficiently it's getting there. Just that, did the car make it? Okay, great. Did the car like kill a person along the way? Bad. You know, not, and I'm laughing about it, but yeah, it's not funny. If you're playing Mario, Mario collects coins and moves towards the destination. That's a positive. Mario bumps into one of the enemies and dies, right? Or loses energy or whatever. Um, Picking up faulty products on a manufacturing line for repairs. The system picks up a faulty product, so it like finds the one that's bad, or it picks up a working product that's okay and calls it scrap, right? So that would be examples. All right, I mean, they have a little example here. You know, if you were to make a humanoid walk, you know, what's a positive reward? Well, you're able to do it and get to where you're going. What's a negative reward? You maybe fall on your face, don't get to where you're going, you know, that type of thing. Right. And we don't have to do all these, but you know, these are things to think about. And this is one, like for playing Tetris, like if you look at the notes of these slides for playing Tetris, it says a positive reward is getting higher scores, demolishing the bricks. Those are positive rewards. Negative would be the bricks reaching the top level, right? And then you get all bricked up and you can't add any more stuff. Another term, state, right? In state basically describes the current situation. So for example, where the robot's legs are right now when it's trying to walk. Or if we're playing a board game, where are the pieces right now? That's the current state. Or where are, or using a self-driving car, where are the pedestrians and other vehicles that you're trying not to hit? You know, what's in the environment? How are things? You know, is a good way to look at the state. What is the state of the current environment that you're in? I'm just noticing here that I think my nightlight just came on my computer, and I don't want it to be on. There we go. Better. Did you guys? I don't know if you caught that in the video, but it's like sometimes I have that turn on at night to help my eyes, but now is not one of those times. Action. So with action, it says describes what the actor can do in each state. So like if you're, let's say you're playing a board game and you decide, okay, I'm going to move this piece. I'm going to put it from here to here, or I'm going to place a piece here. I don't know how Go works, right? Or if I'm playing Tetris and a thing is falling, and I'm like, oh, I can fit it over here. That's the maneuvers you're making to make it fit over there, right? And that's kind of the whole point, right? So what actual thing are you doing in the environment to trigger a reward or a penalty? We also have history and state, where we look back at every time we did something in the environment, what happened? All right, and then we try it again. What happened this time? Where did we end up as a result? And so we're combining those. And it's really, as it says here, it's a collection of observations in a sequence. So like we take an action, we see what happens, we observe it, we notate it, we try something else, we try, and it builds up a timeline, a history, right? Hey, we tried this 20 times and it failed. We tried that one time and it worked. Let's keep trying that one time that it worked. And okay, so when we start to combine this, it states the information used to determine what's the next action to take. And, you know, if we did something and it worked, why wouldn't you try to repeat something similar, right? And what they're telling us here is that ultimately it becomes a function of history, right? So like we can see what the state is, and they give us a formula for it. And I wouldn't get mired too deeply in the formula, more in the concepts. State can be observed or partially observed. And it says here in an observable state, you can kind of see the whole system, right? So a game board would be a great example. Like if I'm playing the game Go or chess or something like that, I can see the whole board and where everything's at. I'm not looking at just a little piece of it. A self-driving car, think about this. If it's driving down the road and it needs to go around a corner, it doesn't really know what's coming up, right? It doesn't have like a top-down view of where it's going. Okay, granted, it could use Google Maps and GPS itself and find its path, but it might not know what obstructions are in the road. See, and that's all part of the state. And so that's kind of the point of a partially observable state is what I'm describing. Kind of know the lay of the land, but we don't know what the current situation is. It says an example of a partially observable state is a card game where you can only view the cards in your hand. You don't know what the other player's holding, what's in the deck, what's the next card to be dealt. You don't know that. You know there's a possibility of getting certain things, but you really only know what you have. When we're looking at these things and we're measuring them, a state can be discrete or continuous. So this is kind of a mathematical thing. So discrete means that is a very particular thing that's going to happen. So for example, if we're in the grid world and I want to move to a different spot in the grid, that's a discrete action. I'm going from this square to that square. In continuous, for information or continuous state, I can be anywhere on that curve, right? I'm not in one particular box. I could be at the very bottom of the dip or part of the way up or a little farther up or just 1 micron farther up. But all that information is continuous. So it's not like this or that. It's not like a black Go thing and a white Go thing. You know what I mean? It could be something in between, right? So continuous. And it says here, normal practice to discretize, and I'm not sure if I'm saying that correctly, the continuous variables, but this will lead to the curse of dimensionality. So in other words, if we took this continuous waveform here, which is really infinite in its detail, and tried to take slices of it to declare a point, it breaks it down. And very interestingly, that's exactly how we digitize audio and video. Audio is a continuous waveform, and we digitize it and take pictures of it and then put the pictures together to make it sound like the audio. But it's not really the audio, right? It's very different. Like if you see music in front of you happening with a real instrument, it sounds way different than a digital recording of it. Yeah. All right. Then we look at the information state, and they call this a Markov state, and it calls it a stochastic model, right? It assumes that the future states depend only on the current state. So we don't look at the past. We look at where we're at currently and where we're going, right? So we're not like the fact that I came from back there doesn't dictate where I'm going forward, right? That was then. Now I might be going straight down the path, or I might go left or right, or somewhere in between, or who knows, right? And since it's not dependent on the previous state, right? So like, in other words, what happened in the past will not dictate what's going to happen in the future. Just because I made a series of bad chess moves doesn't mean my next chess move is going to be a disaster. Well, probably does, but you probably, it doesn't guarantee that, right? So it says, therefore, it contains sufficient statistics of the future. Kind of an interesting thought. All right, policy, and they usually refer to policy in this with the Greek letter P, basically, or pi. So I find that a little confusing. But they're saying that is the strategy an agent uses in pursuit of goals. So it dictates that the actions that the agent takes are a function of the agent's state and environment, right? So like, where are you at? Where's the environment at? And then what's the policy that you've determined as a result of where you're at? So for example, if I'm sitting outside and it's raining, well, my policy might be to have an umbrella, If it's sunny, well, I might still choose to have an umbrella because I don't want to get sunburned. I'll use sunscreen instead. We have the value function, and so basically, these models are based upon, mathematical representations, and it estimates how good an agent is in its given state. So like, all right, so here where we are right now, how good are we? Are we okay, right? And is this put us in a position where we can get rewards out of this position, right? And they map these things, right? So there's basically to the state and the action, and they have two types of value functions. So like the state value function and the action value function, and then enter the complicated formulas that you never want to learn in your life, right? By looking at them. But this is calculus speak here. And, state value function is basically written as a function like this. And it basically refers to expected values that if we follow policy over time, right? And time is always a thing here. So like, in other words, the expectation is that you're trying something and based on our current state, and we try again based on our current state. And every time we try, we're doing it over the course of time. And then we come up with a summary of all of that. The action function is written in like this, but also same thing. This time we're looking at what actions were taken and how that, so, well, I tried doing this and this happened. I tried doing this and this happened. It doesn't necessarily look at what we did. It looks at the action that was taken, right? And the actions that we take over time. Right. More terminology. So we look at the model, right? And here it says whether the agent is using learning through environment actions. Okay, so if yes, it's a model-based algorithm. Okay, so they say like dynamic programming. If not, right? So if it's not learning through the environment, then it is a model-free algorithm. And what they have here are examples, including Monte Carlo control, SARSA, Q-learning, and actor critic. And these are all forms of reinforcement learning, by the way. So dynamic programming is one approach if it has a model. So if it has like a pattern to follow. If it doesn't have a pattern to follow, then we use these other approaches. And that allows us to basically decide how to interact with that environment. All right. So kind of to break down some of the models here, and please don't worry about memorizing this stuff. I just want you to kind of start absorbing some of it, right? So we'll take our reinforcement learning approaches. We break it into ones that have models and ones that don't. And you can see the ones that don't have models, they have all these different algorithms. You notice how like we have policy optimization and Q learning that kind of have some shared approaches that they point to. And then, if we do have models, so like why, here's kind of an interesting question to ponder and maybe help you understand this a little better, is how does AlphaZero have a model? Here's the answer. It has rules to the game. So there's a model to follow. It's not like inventing the game from scratch, like inventing the game board, the pieces and the rules. It's like, here's the game board, here's the pieces, these are the rules. That's your model. And you figure it out, right? Or it has a model, it's not told what it is, and it figures out the model by trying it, right? See the difference? Where if we don't have a model, then we have goals we might try to reach. Like, what is the policy? What thing are we trying to maximize? Our fuel efficiency, our travel time, our cost, right? And so we're trying to optimize those things. Or are we just kind of learning it from scratch? Like what feels best, and we're going to walk that Q learning path here. But I think that I'm hoping that helps to clarify some of it for you guys. All right. So, all right. And this is kind of saying, for example, some of the things I was just saying in a different way. It says in a model environment, the policy is based on machine learning model that we use. Okay, the policy network determines the reinforcement learning. It's important to know fully well that the policy is to decide the action of the agent. So in other words, once again, if you're looking for efficiency, you're trying to maximize it. If you don't have it, we have policy based on the use of machine learning models. Instead, it says a policy is guided by the use of non-ML algorithms, and those can be dictated by observation in physics. For example, if we want to balance that seesaw, assuming that all those little figures weigh the same, right? Like right now, would you think that that's how that seesaw should be balanced? Right, it doesn't seem to make sense. Although maybe the red one weighs a lot more, right? That's a possibility. Maybe this is made out of gold and this is made out of feathers. We don't know, right? But by observing it, we are starting to make assumptions. You see what it is. If they were all the same weight, it should really tilt to the other side, right? And so observation in physics, and how do we adjust that? And the way that we can test it is by moving the things around or switching them around or whatever. Or we have something else does that, we go, oh, I see. And we do that as human beings. Like you just look at something and go, oh, I see how that works. And some people see it and some people don't. Right. All right. Some little chart here to help guide you with negotiating that. In a model based thing, okay, you have to have some sort of a policy. You have to have the rules. What are you trying to do? Fuel efficiency. I'm just using that as an example. We have to, in this approach, since we're using a model, we have to build a model. So we either have to model the data or develop some sort of a rule, and then there's a reward system, and it's counted or accounted for, right? It requires the use of initial states to predict the next state using the policy network. So in other words, we look at the game board and go, this is where we're at and this is where we're going because this is our goal. This is how it works. Model free, we don't have to have a policy. We don't know what we're trying to optimize. So therefore, we can't really rely on modeling. We don't really need it. And the reward really isn't part of it. This is all really kind of weird to think about when you, it's kind of like a logical leap, folks, as you start to think through this stuff. And it doesn't require the use of initial states to predict the next state, right? Because we don't know where we're coming from and where we're going to. But it doesn't mean that you can't reinforce. So, okay. So now we get to this terminology, and I think this one is a really important concept in this area, where we are comparing what we call exploration to exploitation. And I was using this terminology before we kind of even got digging into this tonight. And exploration, it says, means to gather new information, to try out new things in order to see what the potential outcome is, and hoping that you will get a better outcome, right? And you can see here the robot is going down the road. It's got a fork in the road, and is he going to go to the usual place or go to the grand opening? Well, going to the grand opening would be exploring. It's like, maybe the cheeseburger is better at the new place. I'm going to try it. Or the usual place is you just go to QP's because the burgers are great, right? And really greasy and fresh and everything. They serve them on those little plates. Or exploitation, right? So like going to QP's is like, you know what? I get a good burger there every time. Their fries are awesome, so I just go back, and the price is good. And so you already know what the outcome is. So exploitation means I know this is a good outcome in this situation, so I'm going to utilize that. Why not? Right? You want a good burger? If you're in Racine, I go to Cupie's. If I'm in Milwaukee, I go to Cops. If I'm in, I don't know, Burlington, I go to Fred's. That kind of thing, right? I know where the good burger joints are. And if I'm traveling the country, I go to Culver's because I don't know what the good burger joints are in other places. So one is exploitation, one is exploration. I love this little graphic here. This is a great little graphic because here's two guys digging a hole, right? And the one guy digs a shallow hole, finds a big diamond. And the other guy's like, man, I dug twice as deep and I got nothing. And so the other guy leaves, he's got his diamond. So the other guy switches over to the other guy's hole and he keeps digging deeper and deeper and deeper, and he's not finding anything. Meanwhile, he was a half inch away from a super giant diamond because he gave up. He stopped exploring, right? He was trying to exploit what he thought would work. Yeah. So I think this is really kind of a cute little graphic, but it really kind of nails it, right? In terms of the concept here. How do you know what's there if you don't explore? So there has to be encouragement to explore, because maybe there's another burger joint that's even better. Maybe I go to Solly's up in Milwaukee. Right? You guys ever eaten there? That's really super greasy butter burgers. Oh my God, they're so unhealthy probably, but delicious, right? Can't get enough. Drowning in butter and all that stuff. All right. So the point is that you choose between the trade-offs. So at the beginning, we need to do more exploration so we can get better understanding of the environment. And then as we progress, then we will do more exploitation when we know what works in order to maximize efficiency. It's like, I already know what works here, right? And as we proceed, we will lower the percentage of exploration, right? Because we already kind of know some stuff that works, but we're still exploring. But we have, after a while, have figured out what is good and what is not. And they talk about these words, global maxima and not local maxima. So if you haven't really reached what you think is optimal, you keep exploring. So I think, okay, I think we're coming up on a video here. So I think we're at a point where we should take a break. Then we'll watch this little video here because I think it's very helpful in explaining it. It's a little bit longer video. So what we'll do is we'll pause right now our recording. and we'll take our 5-minute break. So we'll come back at about 9 o'clock and we'll dig into this video and then move forward from there. So I'll see you guys in 5. Welcome back, you guys. We are going to watch this video here in just a moment, but we're just going to hit these bullets here. It says choosing between the trade-off of exploration and exploitation. And it says we can use a strategy. So there's approaches to doing this. And basically we'll start by initially exploring. So imagine like you go to a new town. And let's say we use the cheeseburger example. You go to a new town, you don't know what the cheeseburger joints are, right? And so you Google a bunch and you ignore the reviews. You want to make your own decisions, and you just go from place to place. You try all of them, right? And see if you like them or not, right? And then you find some you like, some you don't like. Next time, you're going to do some more exploring. You might reach out and go a little further, go a different direction. But you have the places that you like, and you do like cheeseburgers. So every once in a while, you go back to the ones you like, right? But as you progress, every time you go out, you start to narrow down your choices. So there's a reason why, for example, people have favorite restaurants, right? Why? Because, hey, I tried all those and they weren't very good. Service is bad, the food is bad, they weren't clean, or whatever the situation is. But eventually you do get to the point where you do know where the good ones are. And unless there's something new in the mix, there's no real reason to explore much more unless a place revises something, right? So that's kind of what this is about, to explain that trade-off between those two things. The audio on this is kind of quiet, but the video is really good.
Wix, one platform.
Sorry about the Wix advertising. I'm trying to talk over it, so
unlimited creation.
Push up to your brains. There we go.
What's up, guys? Welcome back to this series on reinforcement learning. Last time, we left our discussion of Q-learning with the question of how an agent chooses to either explore the environment or to exploit it in order to select its actions. To answer this question, we'll introduce a type of strategy called an epsilon greedy strategy. So let's get to it. We're going to pick up right where we left off last time by continuing our explanation of Q-learning with the lizard game example. Remember, in each episode, the agent, the lizard in our case, starts out by choosing an action from the starting state based on the current Q value estimates in the Q table. The lizard chooses its action based on the action with the highest Q value for the given state. Since we know that all of the Q values are first initialized to 0, there's no way for the lizard to differentiate between them at the starting state of the first episode. So the question remains, what action does the agent start with? Furthermore, for some...
Oh, I apologize. And now
we've got passion, we've got determination. Like, and if we
very,
set
very
our
sorry
sights
about
on
that.
something,
So
you better believe it's happening.
Again.
What's up, guys? Starts out by choosing an action from the starting state based on between them at the starting state of the first episode.
Oh
hey,
my
tech
God,
lovers, Dave from Big Tech Barn. Today, it's all about the business.
So the question remains, what action does the agent start with? Furthermore, for subsequent states, is it really as straightforward as just selecting the action with the highest Q value for the given state? Additionally, we know that we need a balance of exploration and exploitation to choose actions, but how exactly this is achieved is with an epsilon greedy strategy. So let's explore that strategy now. To get the balance between exploitation and exploration, we use what's called an epsilon greedy strategy. With this strategy, we define an exploration rate, epsilon, that we initially set to 1. This exploration rate is the probability that our agent will explore the environment rather than exploit it. With epsilon equal to 1, it's 100% certain that the agent will start out by exploring the environment. As the agent learns more about the environment, at the start of each new episode, epsilon will decay by some rate that we set so that the likelihood of exploration becomes less and less probable as the agent learns more and more about the environment. The agent will become, in a sense, greedy in terms of exploiting the environment once it's had the opportunity to explore and learn more about it. To determine whether the agent will choose exploration or exploitation at each time step, we generate a random number between 0 and 1. If this number is greater than epsilon, then the agent will choose its next action via exploitation, i.e. it will choose the action with the highest Q value for its current state from the Q table. Otherwise, its next action will be chosen via exploration, i.e. randomly choosing its action and exploring what happens in the environment. So recall, we first started talking about the exploration-exploitation trade-off last time because we were discussing how the lizard should choose its very first action since all the actions have a Q value of 0 at the start. Well, now we should know that the action will be chosen randomly via exploration since the exploration rate is set to 1 initially. Meaning with 100% probability, the lizard will explore the environment during the first episode of the game rather than exploit it. Alright, so after the lizard takes an action, it observes the next state, the reward gained from its action, and then updates the Q value in the Q table for the action it took from the previous state. Let's suppose the lizard chose to move right as its action from the starting state. We can see the reward the lizard gets in this new state is -1, since, recall, empty tiles have a reward of -1 point. To update the Q value for the action of moving right taken from the previous state, we use the Belman equation that we highlighted previously. We want to make the Q value for the given state action pair as close as we can to the right-hand side of the Belman equation so that the Q value will eventually converge to the optimal Q value, Q star. This will happen over time by iteratively comparing the loss between the Q value and the optimal Q value for the given state action pair, and then updating the Q value over and over again each time the agent encounters this same state action pair. And the objective of this process is to reduce the loss between the Q value and the optimal Q value. To actually see how we update the Q value, we first need to introduce the idea of a learning rate.
It's not just about saving time, it's about expanding what's possible.
The learning rate is a number between 0 and 1, which can be thought of as how quickly the agent abandons the previous Q value in the Q table for the new Q value for a given state action pair. So, for example, suppose we have a Q value in the Q table for some arbitrary state action pair that the agent has experienced in a previous time step. Well, if the agent experiences that same state action pair at a later time step once it's learned more about the environment, the Q value will need to be updated to reflect the change in expectations the agent now has for the future return. We don't want to just overwrite the old Q value though, but rather we use the learning rate as a tool to determine how much information we keep about the previously computed Q value for the state action pair versus the new Q value calculated for the same state action pair just at a later time step. We'll denote the learning rate with the symbol alpha, and we'll arbitrarily set alpha equal to 0.7 for our lizard game example. The higher the learning rate, the more quickly the agent will adopt the new Q value. For example, if the learning rate is 1, the estimate for the Q value for a given state action pair would be the straight up newly calculated Q value and wouldn't consider previous Q values that had previously been calculated for the given state action pair in earlier time steps. Now let's see how exactly the new Q value is calculated using the learning rate. Specifically, we'll see how the Q value is calculated for the example of the lizard taking the action of moving right from the starting state. The formula for calculating the new Q value for a state action pair S, A at time t is this. So our new Q value is equal to a weighted sum of our old value and the learned value. The old value in our case is 0 since this is the first time the agent is experiencing this particular state action pair. And we multiply this old value by 1 minus alpha. Our learned value is the reward we received for moving right from the starting state, plus the discounted estimate of the optimal future Q value for the next state action pair S prime, A prime at time t plus 1. This entire learned value is then multiplied by our learning rate. All of the math for this calculation of our concrete example state action pair is shown here. So take a moment to pause and make sure you've got everything down.
I ordered 200 hand-forged knives to my dorm room and built a Wix website to sell them.
Alright, so now we'll take this new Q value we just calculated and store it in our Q table for this particular state action pair. We've now done everything needed for a single time step. This same process will happen for each time step until termination in each episode. Oh, and speaking of termination, we can also specify a max number of steps that our agent can take before the episode auto-terminates. With the way the game's set up right now, termination will only occur if the lizard reaches the state with 5 crickets or the state with the bird. We could define some condition, though, that states if the lizard hasn't reached termination by either one of these 2 states after 100 steps, then terminate the game after the 100th step. Now, finally, once the queue function converges to the optimal queue function, we can obtain our optimal policy. Alright, now I know all of that was kind of a lot, so I've provided really condensed, summarized steps for everything we covered in.
All right, and the video goes on, and I would encourage you guys to watch it. And I'm very, very sorry, frankly, that those ads pop in. I can't run ad blockers inside my PowerPoint thing, so maybe I should like try a different strategy next time. All right, so to kind of repeat like what she was doing here, there is kind of basically an algorithm here, and what they're giving us is a pseudocode, right? So like the pseudocode, right? So any of you guys that have learned how to code, pseudocoding is often, the first step in writing any computer code, if you're doing it from scratch, especially, so that you know how, you got a problem at hand and you're trying to solve a problem, and what are the steps to solve the problem that will work best every time. And these are basically the steps, right? So like it says generate a random number between 0 and 1. Check if that random number is less than the epsilon. If yes, the agent will explore, right? And randomly choose its action and see what, and it says more likely to happen when the epsilon is high. Otherwise, if it's no, the agent will choose exploitation, and it'll choose the highest Q value for its current state. So like where it knows it's going to succeed, it's just going to follow it. And that's more likely to happen when epsilon is low, right? So if you remember at first, we're going to start with that epsilon value like cranked up. So we want it to explore. You move to a new town, you don't know where the good burger joints are, right? But that number will change as you iterate. So every time you go through the process, you're going to reduce the epsilon manually, right? And then repeat the above steps. So eventually you're going to get to the point where it's almost always exploiting rather than exploring. That's kind of the point of it. All right, so more examples here. All right, so it sounds like my cheeseburger thing. Exploring is drive around town to see where the new places are. Exploitation is I'm just going right to Culver's because I know the burgers are good, right? And you're done, right? Or which society to join. You scan through the available list, or you choose the same one that you did before, right? Or where you're going to build your franchise food joint. Well, you look at random places in town, or maybe in the middle of town because that's how you've been doing things, right? That's worked for you in the past, All right, so they have examples of this, and if you want to answer these on your own, the notes on this slide give you answers for this if you wish. I'm trying to move forward a little bit more quickly here because we do have a lot of material to hit yet. All right, so we also have to talk about prediction and control. And so, so for example, it says prediction, evaluate the future, like what's going to happen. So you're given a policy and you have to measure how well it's being executed and predicted by the total rewards. And it's an ability to estimate the consequences of an action. So it's like, hey, you know what? If you cross the street without looking both ways, there's a good chance you might get hit by a car, right? I mean, that's kind of a given. So control is a little bit different. This is where you're trying to optimize the future. You're trying to find the best way to do it. And you do that by predicting the values by selecting amongst the best actions. And basically it's like, what's going to yield good results. So you choose the best action to yield the result. So for example, it's easier to mow your lawn if you do it more often. If you wait till it gets really tall, then it's really a pain. I know that because when I mow it more often, it's a lot easier, right? And that's just based on experience. So, that's a very simplistic overview of those. Now we're going to start looking at this thing called the Markov Decision Process, which is kind of a precept to Q learning, which is where we're headed here. And what it is it, as it says here, it's a formal way to do sequential decision making, right? And really, it is ultimately the the basis for solving these kind of reinforcement learning problems. And if you guys are wondering where it comes from, this is like, they train a dog that when they ring a bell, they're going to feed it food, right? And because it knows it's going to get fed, it starts to salivate because food's coming. Every time the bell rings, I get food. So I'm like, I'm hungry, right? And so that behavior is reinforced, and it gets to the point where they ring the bell, don't give the dog food, and the dog still salivates because it believes it's going to get food, right? So the things that we look at in this decision-making process are the decision maker, the agent, the environment, the states, the actions, and the rewards, right? All the stuff we've been talking about. The agent will interact with the environment. Each interaction is sequential, and it happens over time. We keep trying it, happens over and over again, and then the agent observes the environment, decides on an action, and is given the reward, hopefully. Right? Ultimately, what we're trying to do is maximize rewards, right? And it says not just immediate rewards. So like we not take an action just to get an immediate reward. Sometimes we figure out that we have to take a series of actions in order to get the reward. So they're cumulative, right? They build up to a great reward. We're still looking at states, actions, and rewards over time, right? And if you want to do the math on it, this creates state action pairs. And every time we run it, we increment the time. That's why we have a little t+1 in here, and then it'll be t+2 and t+3, and it'll iterate, right? And those are state action pairs. Ultimately, we're looking at maximizing the rewards, right, collectively, and hopefully we can do that by maximizing the repeated actions over time. So you see like state and action, right? And these have sub numbers. So those go together, these go together, et cetera, et cetera, et cetera. We have transition probabilities too. So like there are some random things that happen in the situations, and we have, probability comes into play here. So, just because you were successful with an action one time doesn't mean you'll always be successful with an action. There's might be probability of percentage. She was touching upon that a little bit, which is why something didn't necessarily evaluate to 1, it evaluated to 0.7, right? So we look at the preceding state, and then we look at where that's going to lead us. Now, when you start to combine all the probabilities together, it actually starts to form a matrix. So like a table of information, and we call this a state transition matrix, where it shows what happens when we move from place to place to place within the matrix. Now, this is what we call, by the way, like a network diagram. And this is a typical decision-making tool, believe it or not, in like operation science, and business analysts use these kind of tools. And basically, we have what we call nodes of the network, right? And these are like, we're trying to go from here to here to here to here, or whatever. When you're at any given node, you can only move from one spot to another. Ultimately, what you're trying to do is get to the stop node to finish. And every time you travel one of the pathways, there's a value to the pathway. And, I would equate this to like, when I used to teach quantitative analysis, we used to do network shipping diagrams. So for example, like if I'm shipping a pallet of product from New York to California, there's maybe like 1 or 2 obvious routes you think you should take. But in truth, you can travel any road to get there. And when you travel a road, there's tolls you might have to pay, fuel costs, speed, whatever. And you're trying to maximize maybe the speed and save on fuel at the same time. Like you have multiple goals. As you travel from one spot to another, you tabulate these, and there's values, right, to them. And I don't know what is good or bad here. But every possible path that's possible in the network is represented here, and every pathway is given a value. And so here's some of the possible pathways you could follow in this network, right? So I can go from, for example, from the first node back to the first node. And then I go from the first node back to the second. And then I'm like, oh, I forgot something at home. And I go back to the first. then go back to the second, then I could go right to the stop point, or I go to the third one, and then up to the stop point. You know, you can follow all these different pathways, and there's values to the pathways that you calculate. So like if you take the transitions and you look at all the possible permutations to get from here to here, these are some of the possibilities of what might happen, right? And you notice in a couple situations, you go back to the first node and just keep going back to the first node. That's not really a good scenario, but it is possible, right? Like if you were driving a truck and you got part of the way out of town, like, oh shoot, I left my wallet on my dresser at home. I got to go back, you know, and tell me you haven't done that. People do that. But there is a matrix, and how would you draw the transition matrix based on all the possible pathways? This is what we're kind of leading to. So if I was to go from S1 back to S1, so S1 to S1, the value is 0.2, right? If I go from S1 to S2, it's 0.8. So basically, we're just transferring the information from the network back into the matrix, right? And we make a two-dimensional chart out of it. And you can tell that in spots where, like for example, I can't go from S1 right to S3. That's not possible. So that gets a 0. That's not a possible pathway. But the ones that are possible have point values attached to them, right? It says rows and columns explains, you know, outputs from current states to others, inputs to current state from other states. And then now we're summing the values, right, for each row. So in other words, if you look at any one possible row, so the point of this is for all the possible pathways out of S1, they total up to 100% of all the possibilities. Maybe only 20% of the time do you have to go back home and get something you forgot. 80% of the time you're on your way, right? From S2, well, what are the possibilities leaving S2? Well, 10% chance of going that way, 70% chance of going that way, 20% chance of going that way. But in total, S2, all those values add up to 1. That's the point, right? Right. It says some of the values for rows must be 1, but for columns may or may not be. All right, so like if you look at the column here, that's only 0.4, that's only 0.8, that's only 0.7, and that's more than 1, right? And if you kind of go back and analyze this, this is more than 1. Why is that the case? This is really kind of an interesting question, right? Because from S3, where S3 has only got one choice to leave it. You go right to the stop point. So it gets 100%. S2 also has that possibility. But you see how that works. So when you're here, there's only one choice. You're going to end up at your destination. All right. All right. So like if we really had tons of time and I was really cruel, I would make this homework. I would have you draw the matrices for these. And you could do it. Like if you really have that kind of time on your hand, I would encourage you, draw the matrices for these and see. Now, from a practical standpoint, the way that we're going to work is, yeah, we could do this stuff mechanically. And in the old days of operation science of teaching this kind of stuff, we would do that. And frankly, we would also use spreadsheets to do it, right? To develop these matrices. And then you can run formulas and permutations and all this, you know, analysis on it. So this ultimately all leads us into Q learning, as it states, a type of reinforcement learnings. Its inputs are states and rewards, where we're at currently and what reward we're getting. The output from Q learning is action, tells us which way to do it, right? This is based upon the fact that we don't have a model, right? We're not looking at a math-based formula or something like that. And notice number 5, the AI agent doesn't seek to learn the underlying model. It attempts to construct an optimal policy by interacting with the environment. It figures out that maybe the best way from New York to LA is just to take, you know, Interstate 80 to Iowa and then branch down the 70 or, you know, whatever the best path is. There's a route, you know, that's best if you're driving a truck. Q learning uses trial and error, right? So it tries it, that didn't work. It tries different, okay, that worked, right? And it continuously updates what it has learned, right? It has all the basics of reinforcement learning. There's an input-output system. It has an environment that it operates within, and it operates on the basis of the Markov decision process that we just looked at, right? On top of that, it has two additional characteristics on top of the Markov thing. It has a finite number of possible states, right, in which the agent will reside in. So, for example, if I'm going to go from New York to LA, I mean, it's possible that I could go around the world to the east if I could drive it and go all the way around the planet that way to get to LA. You know, not likely, right? We're operating within the environment of the US, for example. So it also has a finite possible number of actions because it's in a finite space, basically. So it only really have so many choices. Like if it's in the US, there's only so many roads you can take to get there. So here's an example, and they call this a normal maze, and it says a finite number of locations. We have a starting point and we have an exit point, right? Any spot on here is a possible location, is a state. And from any one of those points, we can move in principle any direction. Now, but okay, if we're in the start point in the bottom left, really we can only go up and right, right? If we're in the middle of the board, we can go any direction. But if we're trying to get from here to here, I mean, most of us can, I mean, there's no blockades in here. It's very easy to go, oh, I'll just go, well, if my choices are up, down, left, and right, I can't go diagonal because otherwise I go diagonal, 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 right, out, right? But diagonal is not on the table. So I'm going to go right, up, right, up, right, up, right, up, right, right. How many moves is that? Right. Now, notice, every time I go to a different square, it's going to say, okay, that wasn't the exit, so you lose a point. That wasn't the exit, you lose a point. I don't know how many maneuvers I did before, but I think it's like 1, 2, 3, 4, 5, 6, 7, 8, 9. -9 maneuvers. But then I get to here, and then I get a positive 100, and that cancels out that -9, and it ends up with a value of 91, right? Whereas if I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I think the longest possible path, and it was like -50 or something like that. And in fact, keep in mind, I can backtrack and make mistakes. I can make that a really large negative number, and it doesn't make sense to follow that path because the 100 won't cancel it out. So what I'm really looking to do is to optimize the greatest value I can out of the path. And so what would happen, and this is what Python will do for us, the coding, is it'll find that optimal path or paths. There might be plural paths. There might be several paths that are optimal. But it's mathematically based, and there's the reward, is huge, and the punishments are small in this case. So now if you have a little bit more complex situation, what if you have the exit, same kind of board, same kind of scenario? Here's the problem. We have cliffs here. So if I walk into a cliff, I lose 100 points. And as I'm exploring, I might walk off a cliff a couple of times. Now, if I walk off the cliff, right, and I keep like racking up these negative numbers, it doesn't make sense to go there. But anybody can see that basically I'll want to stay in the -1 path, move my way up and around, or up and around and down and over, right? And those would work. And we would explore that. So this is kind of what we're talking about, is it gets into a matrix so that we can determine the moves, calculate the values, and find the optimal solution. And in some cases, sometimes there's multiple optimal solutions, right? Like if I want to drive to California, I'll use that example again. I can take the scenic route. Hey, I stopped and saw the Grand Canyon on the way. It was wonderful. Or I stay on the interstate and get there a little bit faster, right? And save on fuel costs. So they're both optimal. They both got me there. but one might be better than the other depending on what your criteria is or your reward system. Are you trying to save money? Or are you trying to see America? Right? Two different goals. Right? So these are the operating precepts. Right. Ultimately, Q learning is kind of about the Q value. And it says it indicates the quality of a particular action. Right. So we're interested in the highest quality action in any given state. So if I'm like on the board there and I go from here to here, that's not good. We go to here, that's all right. Here to here's all right, not really getting me closer. Here to here, all right, but not getting me closer. So if I was here, this is the best choice. Right, you see, right? And I can do that as a human being just visually, right? But we're going to have algorithms do that. Ultimately, we estimate how much, it says, additional rewards we can accumulate through all the remaining steps so that we can get that Q value up, and the Q values increase as the agent gets closer to the highest rewards. We can have positive or negative encouragements, as we saw, and we use numbers to do that. Ultimately, we build a Q table, and so for every position on the matrix, we can do calculations. So we can say, okay, if we're here, and I know this kind of falls off here a little bit, and I can't like tweak it, but if we're like in this position, if we go up, we get this value. If we go right, we get that value. If we go down, we get this value. If we go left, we get that value, right? And this is not very good because these are negative numbers, right? And so which of these do we take from position one? Which is the best path? Well, the one with the least punishment, right? We would, if we were here, we would go right. And then when you look at that cell, which path do you take? Well, down takes us for a cliff, bad. Left, well, we're losing ground here, so that doesn't make sense. Up doesn't help us either. But this one's got that lowest punishment, so that's the path we follow, right? And then, here, if we go, you see, once again, down gives us no punishment. In fact, if we get there, we'll get a reward. We can't see it because it's off the bottom of the screen, right? So every position has values, and we get this Q table relative to all the possibilities of maneuvers relative to the position in the matrix. I think this is really fascinating stuff that they kind of break it down. And really, when you start to think about it, this is very logical, right? It's not like difficult to understand, but when you look at the formulas, which is on the next slide, it's like, ugh. But remember, formulas exist to explain what's happening in the real world mathematically, so we can do mathematical operations on them, even if they look ugly. Mathematical formulas try to represent the beauty of the real world and what is common that we can see by looking at it this way. Now, a Q table we can write like this as well. So in other words, for cell 00, here's the value for up, here's the value for right, down, and left. So this in and of itself, each position in the matrix has its own little row in this table with values. So this is really kind of what Python's doing in the background. So for each cell, what are the values for the maneuvers that you make? And in some cases, like if you're in cell 2-1, there's nowhere you can really go, right? And that's kind of represented by nil or null, as we usually call it in programming. I think nil is how they say it over on the other side of the pond, as they say. There are temporal differences. And so basically what it says, this is a method for calculating how much Q value for the action taken in a previous state. So the last time we did it, it had its own Q values, its own matrix. So this is where it's weirder, right? And so every time we run it again, it's going to be a different environment, right? We might have different pathways we follow, and therefore we get different Q values, right? And that all gets updated, and this is represented in this formula, right? And then they break down all the little pieces of the formula. I'm not really concerned about doing that. If you guys want to do that, go for it. But in plain English, we run it multiple times. We get different Q values. We look for the ultimate ones, and we do a cumulative combination of all of it. Then we lead to the Belman equation, which they were talking about in the video. And it says it's important in reinforcement learning because it tells us what is the new value to be used as the Q value for the action taken in the previous state. It looks at both the old Q value, that what was done, and where we're moving to. And then we have that learning rate parameter, which defines how quickly Q values are adjusted, like how many iterations, like what's the time frame we're working within, right? And then a breakdown of this formula. And you guys can tell I'm trying to move fast through the material here. All right. So in the sequence, we set up the Q table. We choose an action from the Q table or to explore, right? Using the epsilon greedy thing. Choose the action in transition next state, receive its reward and calculate. And then we update the Q value, loop back and repeat until it reaches a terminal state, right? Then we start with a new initial state, and then we repeat this maybe 1,000 times, right? And then eventually we'll figure out the best way. So in other words, one way to figure out the most optimal route to get from New York to California is to just drive the roads and see what happens, right? Okay, yeah, maybe that's not what you want to do, but that's kind of how this works. All right, so this can be applied to Python code, and the homework that you guys have is very similar to this example that we're going to kind of go through right now. So this is very useful for the homework. All right, so white tiles, it says here, are safe movable steps. So I can go from any one of those to another without a problem. Then we have a cliff, right? That's a dangerous area, so we want to avoid it. And then ultimately, we're trying to get to the goal, right? Your goal is given a starting point to find the shortest path to the goal. All right, that seems pretty intuitive. All right, so first we create the board. So we create the matrix, if you will. And we initialize all four directions, up, down, left, right. And it says the question, what is the Q values at this stage? Well, we don't know, but basically they're nothing, right? Because we haven't done anything yet. That's really the answer. But you notice in the code, we're zeroing out everything, right? Rows, columns, all that. We define the actions, so we tell it what we're calling them, up, right, down, left. And then we're, in here, at least symbolically, 0 is up, 1 is right, 2 is down, 3 is left, right? And because we're putting it basically in a Python list, we can use the index numbers basically to number them. So 0, 1, 2, 3. So that's kind of a convenience of working with a data structure like that in Python. Okay, so it says initialize the rewards. Initialize with -1 for the white tiles. We were kind of doing that. We assign +100 for the goal, and then whatever you want for the cliff, right? Those are the no-goes. And we were doing -100 for those, right? And you'll notice here, so the first thing they do is they take all the rows and columns and set them to -1. Then we set up the reward, right? And then also we will set up the punishment. So we're taking cell 1, 4, rewards, 1, 4. So this is like a 2-dimensional matrix, right? So, or a list of lists, if you will, and give that a value of 100, right? We also set up all the cliffs, so there's multiple ones, and you just take the positions of all of them and set them up that way, right? And this is a really great example for the homework once again. So here's a cliff in position 2, 0, right? 2, 0, set that to -100. In row 0, we have one in position 0, 3, 0, 3, -100. And so we're just giving those all values. And then we're ready to start doing it. So like we have some helper functions that we'll be using, right? And starting location is terminal state. So are we done? What's the next action? What's the next location? And what's the shortest path? And ultimately, that's really what we're looking for. We check to see first if they're terminal states. Like, in other words, did we reach the end of it? The end of it might be the cliff or the goal, right? And so we're looking. And so if you read the code here, if the rewards of the current position, row and column index, equal -1, it's not a terminal state. So we return false. If it's not, then we return true, and we basically reach that position. So the empty spots are okay to move to, so we're not terminal yet. The other two are not, so we are at terminal state. And that's just a true false to say, did we get there? Did we die, or did we succeed? We can get the starting location, and this can be randomized. And so right here, they're randomizing the starting position with this code. And then while it's in the terminal state, so we're checking that once again. And if it's in a terminal state, then we keep moving and returning that. So it says, define a random starting point, must be on the white tiles. If not, then we're on a goal or a cliff. So let's choose a different random point. That's the point. So you can't start on a cliff and you can't start at the goal. You have to start on one of the white ones. This code enforces that. Then we get the next action. So then we get that random number. We compare that to epsilon. The random number is how much of a percentage are we doing for exploring? How much are we doing exploiting, right? And so if that random value is less than the epsilon, all right, well, then we keep doing it, right? We move on. Otherwise, we get a new random action. So if it's lower, we exploit. If it's higher, we explore. We talked about this already. All right, get next location. This is a little bit more complicated. There's more of a if-else statement going on here. And so like if you start at any particular point, we have to figure out how we can move to the next point. So in some situations, like for example, if I'm here, I can't go up and I can't go left. Those are excluded. So that's represented in this code, right? So I can go up if the current row index is greater than 0. So if I'm on row 1, I can go up. If I'm on row 0, I can't go up. That's what that's telling me, right? This code is pre-configured, for example, in things. But it basically helps us to define the environment. So like if we're at the top, we can't go up. If we're at the left, we can't go right. If we're at the right, we can't go more right. And if we're at the bottom, we can't go more down, right? So all of those are at play, and those are set through these statements. So this is just straight up coding logic, right? And then notice what they're doing here is, they're setting the parameters of what's possible just with very simple numbers and indicators, right? And we could break the code down all the way, but time is just about gone. So we also have the get the shortest path function, and this one also basically operates like this. And I'm not going to read through the code on this one. It says check if the starting point is valid. Okay, so you're not on a goal, you're not on the cliff. You create the empty list, update the current location, move to the next location, update the new location, and you keep going until you reach the goal or the cliff, right? And that's what this code does. And ultimately, this is kind of the learning part of it, right? So this is, not super complicated code, folks. And this is really kind of what I like about this Q learning thing, is it's actually fairly simplistic. Next, there is some training of the AI model. So it says we look at these two tasks, initializing the parameters and then training the models. And so there's 3 parameters, the epsilon, right? The discount factor and the learning rate. And I want you to notice the descriptions here. The epsilon, the percentage of time we should take the best action, right? So in other words, are we doing the exploit? or are we doing the explore, as a percentage? So the discount factor for all future rewards. So when we iterate, the Q values change, right? And then the learning rate, and this is the rate at which the AI agents learn, and it's like, it's set for 0.9 in this case. Right? And those can be varied, but then ultimately we will reiterate 1,000 times or something like that. We do the next action, go to the next location, get the reward and the temporal difference, update the Q values, and repeat, and repeat, and repeat. And it'll keep going. And this will be, if you guys remember your Python loops, right? This will run 1,000 times. It'll keep doing it. And then when it's all done, trying it, it'll give you a message saying the training is complete. Now, to find the shortest path, you're given 3 different starting locations, and that's the homework's the same way. And they're plotting them on the screen there. You find their respective routes, and really, you should be able to visually do this, right? Like from 2, clearly the best route is down, right, right. From 3, okay, well, that one's a little more challenging because I could go this way or I could go this way, right? But I think if you counted the number of squares, this is a shorter path, right? And then you have this one, that's probably the only path you can take. So sometimes you have multiple paths, in which case you choose the shortest, and then you have to ask, are they really the shortest path? The only way to really know is to try that. And notice that the get the shortest path function will allow you to just put in the points and then tell you what the shortest path is. And then this is the output of that, which is the Q values that align to the matrix. And notice here, these are lists of lists of lists. This goes like 3 dimensions deep, basically. And it shows you what these values are. Now, if you look at the notes on this slide, right, and I have them here on my other screen, and I'm kind of looking at them. And I'm not sure that, okay, you know what? I'm going to jump out of presentation mode here. And here, let's do it like this so we can see the notes, right? Okay, so each big chunk refers to the specific row. Example, first chunk, this big chunk up here refers to the first row. Within each chunk, each row refers to the specific column. Example, the first chunk refers to the first column. The first row refers to the location. So the very first row is position 0, 0. Hence, the third chunk, fifth row refers to position 2, 4. So these correlate to the matrix directly, right? So within each one of these entries are up, down, right, and left, up, down, right, and left, cell by cell. If the tiles are at goal or cliff, right, what's the value? 0. If the action will lead to a cliff, the value is -99 or -100, right? So this would lead to a cliff. That would lead to a cliff, right? The objective is to find the action with the highest Q values or positive numbers, right? And if you look at like squares that are empty or whatever and positive numbers, those are good Q values. And it tells us that's where we should be heading. So they have a couple of exercises here to have you, basically try the code. And of course, we're not doing that here in class. That's something you guys are going to do on your own. So I want you guys to work with those notebook files that came with and try some of this and experiment with it. It is acceptable to use generative AI to help you with this work if you want. I also am in full realization that we're not getting to this material here tonight. So I think what I'm going to do is I'm going to record an auxiliary video for this so that we don't have to go to it next week. But this is pretty interesting, and I may throw in an extra credit exercise on this one. I'm still kind of wrestling with that thought. But I will record a video talking about these topics because, if you guys look, we're on slide 96 and there's a bunch left to go. And there's no way, obviously, we're doing that here tonight. All right, folks. So for next time, we will be moving into Unit 10, and I will have new content posted in there soon. And if you guys, once again, if you get stuck on coding or need help with it, please reach out. Videos will post within a day or so. And have a great night, everybody, and we'll see you next week.